In this video, we're going to introduce another important concept in bottom-up parsing, the notion of a handle. To review, bottom-up parsing uses two kinds of actions. We have shift moves, which just read one token of input and move the vertical bar one to the right, and reduce moves, which replace the right-hand side of a production immediately to the left of the vertical bar by a production left-hand side. So in this case, the production must have been A goes to XY. And also reviewing what we did in the last video, the left string can be implemented by a stack where the top of the stack is marked by the vertical bar. So shift pushes a terminal onto the stack and reduce pops 0 or more symbols off the stack, and that's going to be the right-hand side of some production. And then it's going to push one non-terminal onto the stack, which is the left-hand side of that same production. And the key question in bottom-up parsing, and one that we haven't addressed at all yet, is how do we decide when to shift and when to reduce? So let's take a look at this example grammar, and let's think about a step of a parse where we've shifted one token onto the stack. We have int on the stack, and then we have times int plus int still to go that we haven't seen yet. Now at this point, we could decide to reduce by t goes to int, because we have the production t goes to int right here. And so we could then get into this potential state, or this particular state, where we have t on the stack and then the rest of the input that looks like that. But you can see that this would be a mistake. There is no production in the grammar that begins t times. There's no production up here that looks like t times. And therefore, if we were to make this move, we would get stuck. We could continue to do reductions, to rummage around in the string, but we would never be able to get back to the start symbol because there is no way to deal with a substring that has t times something in it. So what that shows us is that we don't always want to reduce just because we have the right-hand side of a production on top of the stack. To repeat that, even if there's the right-hand side of some production sitting right there on top of the stack, it might be a mistake to do a reduction. We might want to wait and do our reduction someplace else. And the idea about how we decide is that we only want to reduce if the result can still be reduced to the start symbol. So let's take a look at a rightmost derivation. So beginning with the start symbol, we get to some state after some number of steps. Remember, that means just an arbitrary number of steps. We get to some state. X is the rightmost non-terminal, and then the next step is to replace X by the right-hand side of some production. And remember, again, with bottom-up parsing, the parser is actually going in this direction. Okay, so this is the reduction direction. And we talk about the derivation direction, the production direction, because that's the easiest way to talk about what strings are derived. We want to begin with the start symbol, but the parser is actually going against the flow of these arrows. Anyway, if this is a rightmost derivation, then we say that alpha beta is a handle of alpha beta omega. And that just means that yes, it would be okay in this situation to reduce beta to x, that we could replace beta by x because it's not a mistake. We can still, by some sequence of moves, get back to the start symbol, by doing more reductions. So handles formalize the intuition about where it is okay to do a reduction. A handle is just a reduction that also allows further reductions back to the start symbol. And we clearly only want to do reductions at handles. If we do a reduction at a place that is not a handle, even though it looks like it's the right-hand side, or may actually be the right-hand side of some production, that doesn't mean that it's actually a handle, and we might, if we reduce there, we may get stuck. So all we said so far is what a handle is. We've defined a handle. We haven't said anything about how to find the handles. And actually, how we find the handles is going to consume much of the rest of our discussion of parsing. At this point, we know enough to state the second important fact about bottom-up parsing. So in shift-reduce parsing, handles appear only at the top of the stack, never inside. And in fact, this is what justifies using a stack, because that string to the left of our focus point, we know that all the action will take place immediately to the left of the focus point. We won't have to dive down into the string to look at its innards, and therefore a stack will be sufficient. So here's an informal proof that handles only appear at the top of the stack, and this is by induction on the number of reduce moves. So this is true initially because the stack is empty, and so we don't. So the only possible reduction is at the top of the stack if there's an epsilon move to make. And immediately after we reduce, the rightmost non-terminal is going to be on top of the stack. So immediately after we perform a reduction, we have our stack, and then we have a non-terminal, and then our vertical bar, and this is the rightmost non-terminal. And since this is a rightmost derivation, that means that the next handle has to be somewhere to the right. The next handle has to include something that, possibly it includes some of this stuff, but it's either right here at the current focus point or it's to the right, because we can't be doing any reductions to the left of the rightmost non-terminal. And so it's going to require a sequence of shift moves to reach the next handle. So once we have this non-terminal on top of the stack, it is by definition the rightmost non-terminal, and so the next handle has to be somewhere to the right of that. Therefore, in shift-reduce parsing, handles always appear at the top of the stack. Handles are never to the left of the rightmost non-terminal, and this is why shift and reduce moves are sufficient. The shift move only moves the vertical bar right because we never need to move it left. And bottom-up parsing algorithms are based on recognizing handles. So as we saw in the example at the beginning of this video, just because you have a right-hand side on top of the stack, that doesn't mean that it's a handle. And so we need to be smarter about where we perform our reductions. Welcome back. In this video, we're going to talk about the key ideas behind techniques for recognizing handles. There is good news and bad news when it comes to recognizing handles. The bad news is that there is no known efficient algorithms that recognizes handles in general. So for an arbitrary grammar, we don't have a fast way to find the handles when we're parsing. The good news is that there are heuristics for guessing handles, and for some context-free grammars, for some fairly large classes of context-free grammars, these heuristics always identify the handles correctly. We can illustrate the situation with a Venn diagram. If we start with a set of all context-free grammars, then the unambiguous context-free grammars are a subset of those. And then an even smaller set are what are called the LRK grammars. And here, just to remind you, L stands for left to right scan, R stands for rightmost derivation, and K stands for the number of tokens of look ahead. Now, the LRK grammars are one of the most general deterministic families of deterministic grammars that we know of, but those aren't the ones that are actually used in practice. Most of the bottom-up tools that are practical use what are called the LRK grammars, which are a subset of the LRK grammars. And then what we're going to talk mostly about is a simplification of those called the simple LR grammars, or the SLRK context-free grammars. And these containment relationships are strict. That is, there are grammars that are LALRK, but not SLRK for every K. And similarly, there are grammars that are LRK for every K that are not LALRK. As we've already said, it's not obvious how to detect handles. So what does the parser know? Well, it sees the stack. At each step, it knows the stack that it has already constructed. And so let's see how much progress we can make just thinking about what information we can get from the stack. So here's the definition. We're going to say that alpha is a viable prefix if there is some omega such that alpha bar omega is a configuration, a valid configuration of a shift-reduce parse. Now keep in mind that the alpha here, this is the stack, and the omega here is the rest of the input. And what does that mean? That means the parser knows this part. The parser knows alpha. It doesn't know much of omega. It can do some look ahead. It can look at a small prefix of omega, usually just one token. But it certainly doesn't know the whole thing. So what does a viable prefix mean? Well, a viable prefix is a string that does not extend past the right end of the handle. And the reason we call it a viable prefix is because it is a prefix of the handle. So as long as the parser has viable prefixes on the stack, no parsing error has been detected. And really, the definition is just giving a name to something. It's not anything very deep. The fact that alpha bar omega is viable, that's just saying that we haven't encountered an error, that this is some state of a shift-reduced parse. It hasn't said yet how we're going to identify it or anything like that. It's just saying that these are the valid states of a shift-reduced parse. Now, the definition is useful in one way, is it brings us to the last important fact number 3 about bottom-up parsing. And that's that for any grammar, the set of viable prefixes is a regular language. And this is really an amazing fact, and one that's going to take us a little while to demonstrate. But this is the key to bottom-up parsing. At least all the bottom-up parsing tools are based on this fact, that the set of viable prefix can be recognized by a finite automaton. So we're going to show how to compute this automaton that accepts the viable prefixes, but first we're going to need a number of additional definitions. The first definition we need is the idea of an item. Now, an item is a production that just has a dot somewhere on the right-hand side. So here's an example. Let's take the production T goes to open paren, E close paren. What we're going to do is we're just going to put a dot in every possible position on the right-hand side. So we'll have one item where the dot is all the way at the left end. We'll have one where the dot is all the way at the right end. And then we'll have items where the dot is between every pair of consecutive symbols. So in this case, there are 4 items for the production. One special case is what do we do with epsilon productions? Well, for an epsilon production, there are no symbols on the right-hand side. We'll just say there is one item, x goes to dot. And these items, you'll see them referred to if you look in help pages and in the literature as the LR0 items. Now we're ready to discuss how we recognize viable prefixes. And the problem is that the stack has only bits and pieces of the right-hand sides of productions in general. Most of the time, we don't have a complete right-hand side on top of the stack. Most of the time, we only have a part of a right-hand side. And it turns out that what is on the stack is actually not just random. It actually has a very special structure. And these bits and pieces are always prefixes of right-hand sides of productions. That is, in any successful parse, what is on the stack always has to be a prefix of the right-hand side of some production or productions. Let's take a look at an example. Let's consider the input open paren, int, close paren, and here's one of our favorite grammars. Now, this configuration where I have open paren E on the stack, remember that this is our stack, and we have the close paren in the input. This is actually a state or a valid state of a shift-reduced parse. And you can see here that open paren E is a prefix of the production T goes to open paren E close paren. And after we shift the remaining close paren onto the stack, then we'll have the complete right-hand side and we'll be ready to reduce. So this is where the items come in. The item T goes to open paren E dot close paren. This describes this state of affairs. It says that so far we have seen open paren E of this production, and we're hoping in the future to see the close paren. So another way of thinking about it is that this item records the fact that we're working on this production, and that so far we've seen this much. Everything to the left of the dot is what we've already seen and is what is on the stack. And what is to the right of the dot is what we're waiting to see before we could possibly reduce. And we may or may not see that. Remember, the parser doesn't know the input. In this case, of course, it's the very next symbol, and so it can see it in the look ahead. But at this point in time, the parser doesn't know for sure what's coming up, and and if this dot were further to the left, there might be many, many more symbols that we had to go before we could perform the reduction. So anyway, what's to the left of the dot records what we've already seen, and what is to the right of the dot says what we're waiting to see on the stack before we can perform a reduction. And now we can talk about the structure of the stack. So as we said, it's not just arbitrary collections of symbols. In fact, it has this very particular structure. So the stack is actually a stack of prefixes of right-hand sides. So the stack always has this organization where there's a bunch of prefixes stacked up, literally stacked up on the stack. And what's going to happen is that the ith prefix, if we were to pick a prefix out of this stack of prefixes, well, that must be the prefix of some production, okay, the right-hand side of some production. And what that means is that that prefix, that ith prefix on the stack, will eventually reduce to the left-hand side of that production. So it'll eventually reduce to xi in this case. And then that xi has to be part of the missing suffix of the prefix that is below it on the stack. So if I look at the previous prefix, the one that's right below prefix sub I on the stack, then when I perform this reduction, that xi needs to extend that prefix to be closer to a complete right-hand side of that particular production. Okay, so in particular, there's going to be some production that is going to already have a portion of its right-hand side on the stack, so prefix sub I minus 1, and xi is going to extend that prefix, and then there's going to be some more stuff possibly that we're waiting to see even after the xi is put there. And recursively, all of the prefixes above prefix k eventually have to reduce to the missing part of the right-hand side of prefix k, the alpha k that goes on the right-hand side. All right, so I have this image that you have a stack of prefixes. We're always working on the topmost prefix on the stack. So we'll always be working here at the right end, shifting and reducing. But every time we perform a reduction, that has to extend the prefix immediately below it on the stack. And when a bunch of prefixes have been removed from the stack through reductions, then we get to work on the prefixes that are lower in the stack. So let's illustrate this idea with an example. So here is another input string. We're going to use the same grammar. You can rewind if you want to see the grammar again. But let's consider this state where we have open paren int star on the stack, and we have int close paren remaining in the input. Okay, and so what items would record? What is the stack structure here, and how do the items record it? Well, let's start here at the bottom. Let's actually work from the bottom up. So we have int star at the top of our stack. So this is the right-hand side that we're currently working on. And that would be a prefix of this production. T goes to int star t. Okay. So what this says is that we're looking, we've seen int star so far, and we're waiting to see t. Now, I'm not showing the items, but I'm just showing the productions that this is eventually going to use. Now, the one that's below it here, the prefix that's below it on the stack is right here in between the open paren and the int. This one's an interesting case. It's actually epsilon. So there's nothing there now on the stack. But eventually, once the int star has reduced to t, okay, then that t is going to reduce to e. And currently, of course, there's not a t there at all. So we've only seen epsilon. We've seen none of the prefix of this production on the stack. And then for the last production, the one deepest in the stack, we've currently seen an open paren, and we think we're working on this production. T goes to open paren, E close paren. All right, and so when this E is produced, that will extend this right-hand side. And now we can record all of this with the stack of items. T goes to open paren dot E, E goes to dot T, and T goes to int star dot T. Okay, and it just records what we said on the previous slide, that so far we've seen the open paren of this production, we've seen nothing yet of the right-hand side of this production, and we've seen int star so far of this production. And just notice how the left-hand side of each of these productions is going to eventually become part of the right-hand side of the right-hand side of the production we're working on, just below it in the stack. So when we've reduced this int star t to t, that will extend to this production, and when that reduces to e, that will extend this production. To summarize this video, we can say a little more precisely how we go about recognizing viable prefixes. The crux of the problem is going to be to recognize a sequence of partial right-hand sides of productions where each of those partial right-hand sides can eventually reduce to part of the missing suffix of its predecessor. Next time, in the next video, we're going to actually give the algorithm for implementing this idea. In this video, we're finally going to come to the technical highlight of bottom-up parsing. So after all the definitions of the previous videos, now we're actually going to be able to give the algorithm for recognizing viable prefixes. So let's dive straight into the algorithm. The first step really is just a very technical point, and it's not that important, but we're going to do it anyway because it makes things simpler, is to add a dummy production. S prime goes to S to our grammar of interest G. So just to set the stage here, we're trying to compute the viable prefixes of G. We're trying to come up with an algorithm for recognizing the viable prefixes of G. If S is the start symbol, we're just going to make up a new start symbol, S prime. So S prime will be the new start symbol of the augmented grammar. And there's just one production for S prime goes to S. All right, so this just allows us to know exactly where our start symbol is used. In particular, our new start symbol S prime is only used in one place on the left-hand side of this one production. And that just makes things a little bit simpler. Now, recall what we are trying to do. We claim that the set of viable prefixes for a given grammar is regular. And so what we're going to do is we're going to construct a non-deterministic finite automaton that recognizes the viable prefixes. Okay? And the states of this NFA are going to be the items of the grammar. Now, the input to the NFA is the stack. So the NFA reads the stack, okay? And then so let's just indicate this. So the NFA is going to take the stack as an argument, and it's either going to say, yes, that's a viable prefix, or no. And it's going to read the stack from bottom to top. So it's going to start at the bottom of the stack and read towards the top of the stack. And our goal here is to write a non-deterministic finite automaton that recognizes the valid stacks of the parser. So that's how we'll know that our parser hasn't encountered any parse errors, because this automaton that we're going to construct will always output either yes, this stack is okay, meaning it could wind up parsing the input, or no, what we've got on the stack now doesn't resemble any valid stack for any possible parse of any input string for this grammar. Okay, so let's think about what we need the moves of this machine to be. So let's say that we're in the state E arrow alpha dot x beta. Now what does that say? So that says that so far we've seen alpha on the stack. Okay, so remember, the machine is reading the stack from bottom to top. This records the fact that the machine has already seen alpha on the stack. So what would be an okay thing to see next on the stack? Well, if this is a valid stack, if having alpha on the stack at this point is valid, well then certainly it would be okay if the next thing on the stack was an x. So we have a transition that if we're in this state where we are working on this production and we've seen alpha on the stack, if the next thing is an x on input x, then we can go to this state where now we record the fact that we've seen alpha x on the stack and we're waiting to see the remaining portion beta of that production. Okay, so this is one kind of move that the non-deterministic finite automaton can make. And again, we add this kind of a move for every item. So for every item in the grammar, if the dot is not all the way at the right end, then there will be a move like this where the dot moves over for whatever symbol happens to come to the right of the dot. The other class of transitions are the following, and these are the more interesting ones. So let's say that we're in this configuration here, where again we've seen alpha, and then the next thing on the stack is x. And here, x is a non-terminal. And I should have said that in the previous case, x was either a terminal or a non-terminal. So this x here is any grammar symbol, not just a non-terminal. But this number 4 here, the moves here at part 4, are specifically for non-terminals. Okay, so anyway, if x is not on the stack, okay, let's assume that we've seen alpha, and then the next thing on the stack is not x. Well, is it possible that there could be a valid configuration of the parser where we saw alpha, but then x didn't appear next? And the answer is yes, because, as we said before, the stack is a sequence of partial right-hand sides. So it could be that all that's on the stack right now for this production is alpha, and that the next thing on the stack is eventually going to reduce to x. Might not be x itself, it might be something that will eventually reduce to x. Well, what does that mean? Well, that means that whatever is there on the stack has to be derived from X. It has to be something that can be generated by using a sequence of X productions, because eventually it's going to reduce to X. So for every item that looks like this, and every production for X now, we're going to add the following move. We're going to say that if there's no X on the stack, well, then we can make an epsilon move. We can just shift to a state where we try to recognize the right-hand side of something derived from X. And these are the only two kinds of moves. Either the either the grammar symbols we're looking for are there on the stack, and we extend the prefix of a right-hand side. So this rule here extends a prefix, says, yes, we see more of that production on the stack, or it tries to guess or tries to discover where the ends of the prefixes are. So if alpha is as much of the production that is on the stack currently, well, then this must be, this X here must, this point here must mark the start of another right-hand side in our stack of right-hand sides, and we would expect to see something derived from some production for X. Two more rules. Every state in this automaton is going to be an accepting state. That means that if the automaton manages to successfully consume the entire stack, then the stack is viable. And just notice that not every state is going to have a transition on every possible symbol. So there will be plenty of possible stacks that are rejected simply because the automaton gets stuck. And finally, the start state of this automaton is the item S prime goes to .s. So remember, the states of the machine are the items of the grammar, and this is why we added this dummy production, is just so that we could conveniently name the start state. So now let's consider one of our grammars that we've been using a lot. So this is the grammar, and now we're going to augment it with the extra production, S prime goes to E. And let's take a look at the automaton that recognizes the viable prefixes of this grammar. And here it is. And as you can see, it's rather large. It has a lot of states and a lot of transitions. And I just want to show it to you here before we describe how we calculated it, just so you get an idea that these automata for recognizing viable prefixes for grammars are actually quite elaborate. But now let's break this down and see how it was produced. So let's begin with the start state for this machine. So we have S prime goes to dot E, and remember what this says is we want to be able to reduce to the start symbol, to our new start symbol, and so we're reading the stack and we're hoping to see an E on the stack, but if we don't, then we'll be happy to see something derived from E. So what transitions can we make from this state? Well, one possibility is that we do in fact see an E on the stack, and in that case the dot simply moves over saying, yes, we've read the first item on the stack, or we've read the E on the stack, and so we've seen the full right-hand side of this production. Now, that would indicate that we were probably done with parsing. This is the state that you would reach after you'd read the entire input and successfully parsed it. You would have reduced to the old start symbol and be about to reduce to the augmented, the new start symbol. But if you're not so fortunate as to see an E on the stack, then you need to hope that you'll see something derived from E. And there are a couple of possibilities there. One is that we could see something that would eventually use this production, E goes to T. And since we haven't seen any of it yet, we put the dot all the way at the left, indicating that we're hoping to see a T, which could then reduce to E, which could then reduce to S prime. Now, if we don't see a T on the stack by itself, the other possibility is that we could be working on this production, E goes to T plus E. And again, we haven't seen any of it, so the dot goes on the left-hand side. And now notice how we're crucially using the power of non-deterministic automata. So here we don't know which production is going to, which right-hand side of a production is going to appear on the stack. And in fact, notice that these productions are not even left factored. So we don't know whether there's going to be just a T there or a T plus E. But we just use the guessing power of the non-deterministic automaton. Let it choose which one to use. And remember, the non-deterministic automaton accepts if any possible choice accepts. So it can always guess correctly. So intuitively, it will be able to pick the right one. Now, of course, we can compile this down to a deterministic machine that won't have to make any guesses. But at this level, where we're writing the non-deterministic machine, it's extremely useful not to have to figure out which of these two productions to use. We can just try both and see what happens. Now let's focus on this state. E goes to dot t. What are the possibilities there? Well, one possibility is that we see a t on the stack. And then we've seen a complete right-hand side. And notice how when the dot moves all the way to the right-hand side, that is going to indicate that we're ready to do a reduce. So we'll talk about that a little bit later, but essentially that's how we're going to recognize handles. When we finally reach a state where the dot is all the way to the right-hand side, that's going to say, this could be a handle that you might want to reduce. Now, if we don't see a t on the stack, then we need to see something derived from t, and there's a couple possibilities, a few possibilities there. One possibility is that it's going to be the production t goes to int. So since we're just starting on this production again, we just put the dot all the way at the left. Another possibility is that we're working on t goes to open paren e close paren. And a third possibility is that we're working on t goes to int times t. And in each case here, notice that the dot is all the way at the left, indicating that we're just getting started. We haven't actually seen any of the right-hand side yet. Now let's shift our focus to this production. E goes to dot t plus e, this item, excuse me. One possibility is that we see an e on the see a t on the stack, okay, in which case the dot just moves over. And the other possibility is that we see something derived from t, in which case we will go to one of the states that begins a t production. And notice here that we already have all three of those items in our automaton. We're just going to states that we went to from the item e goes to dot t. So this item, e goes to dot t plus e, can also move to those three states. Now let's focus on this item here. T goes to dot open paren e close paren. Well, there's only one possible move here. So this is only a terminal. It's not a non-terminal. So there's not going to be any possibility of having something derived from open paren. We just have to see the open paren in the input. So there's only one possible transition here, which is that we see the open paren, on the stack, and the dot just moves over. Now from this state, once again, the dot is next to or just to the left of a non-terminal. So here we might either see that non-terminal on the stack, or we might see something derived from that non-terminal. Well, if we see the non-terminal on the stack, then the dot just moves over, and we get t open paren e dot close paren, indicating that we've seen both an open paren and an e on the stack, and we're still waiting to see the close paren. But we might also see something derived from e. Okay, and so we have these two transitions to the two items that begin productions for e. All right, now let's focus on this state. T goes to open paren e dot close paren. Well, again, because it's a terminal that the dot is next to, is only one possible move. We have to see that open paren if we see anything at all. And we'll wind up with the item T goes to open paren e close paren dot. And now we've recognized the entire right-hand side of that production on the stack. Let's take a look at this item. So here, because the terminal symbol, the only possibility is to read that terminal symbol on the stack. So this would be the next item. E goes to t plus dot e. Focusing on that item again, we could possibly see an e on the stack. All right, in which case we would have recognized the entire right-hand side of this production. We'd have e goes to t plus e dot. Or we could see something derived from e, in which case we'll make a transition back to one of those two states. Now, where have we got productions left to go, or items left to go? Here, we got t goes to dot int, so we would have to see an int next on the stack, and that would be the full right-hand side of that production. Down here, we still have t goes to dot int times t. So again, there's a terminal symbol here, int, and so that would be the next thing we would need to see on the stack for this production to remain viable. And once we've seen the int, we would like to see the times. So we'd wind up in this state, and now we've got the dot next to t. So again, one possibility is that we see the t on the stack, and then we've seen the full right-hand side of this production. But we might only see something derived from t. The t might not be there yet. It might be in a state where we're still waiting for the t to appear through some sequence of reductions. But then we would need to see something derived from t. In this case, we would make a transition to one of the three states that begin the productions for t. And that's the full automaton. Those are all the states and all the transitions for the automaton that recognizes the viable prefixes of this grammar. In this video, we're going to use our example automaton for recognizing viable prefixes to introduce one more idea, the idea of a valid item. To refresh your memory, here's where we left off last time. This is the complete non-deterministic automaton for recognizing the viable prefixes of the example grammar. And using the standard subset of states construction, we can build a deterministic automaton that is equivalent to the non-deterministic automaton. So here's the deterministic automaton that recognizes exactly the same language. This deterministic automaton recognizes the viable prefixes of our example grammar. But now notice that each state is a set of items. So there's a set of non-deterministic automaton states in each of these states. And recall that what that means is that the non-deterministic automaton could be in any one of these states. And in particular, this state here is the start state because it has the item S prime goes to dot E. The states of this deterministic automaton are called variously the canonical collections of items or the canonical collections of LR0 items. If you look in the Dragon book, it gives another way of constructing the LR0 items than the one that I gave. Mine is somewhat simplified, but I think also a little easier to understand if you're seeing this for the first time. Now we need another definition. We'll say that a given item is valid for a viable prefix alpha beta if the following is true. That beginning from the start symbol, this is our extra start symbol, and by a series of rightmost derivation steps, we can get to a configuration, alpha x omega, and then in one step, x can go to beta gamma. And what this says is that after parsing alpha and beta, after seeing alpha and beta on the stack, the valid items are the possible tops of the stack of items. That we could, that this item could be the termination state of the non-deterministic automaton. A simpler way of explaining the same idea is that for a given viable prefix alpha, the items that are valid for that prefix are exactly the items that are in the final state of the DFA after it reads that prefix. So these are the items that describe the state after you've seen the stack alpha. Now, an item is often valid for many, many prefixes. So for example, the item t goes to open paren dot e close paren is valid for all sequences of open parens. And to see that, we can just look at our automaton and confirm that if we see an open paren, remember this is the start state, so if we see an open paren, we take this transition, we wind up in this state here, and then every open paren we see, we just go round and round in this state. So if I have a sequence of 5 open parens as my input, then I'll have transitions 1, 2, 3, 4, 5, all looping in this state, and notice that this item is is one of the items in that state, and that just says that this item is valid for any prefix, or for, excuse me, any sequence of open parens. In this video, we're finally going to give an actual bottom-up parsing algorithm. In particular, we'll talk about SLR, or simple LR parsing, which will build on the ideas of valid items and viable prefixes that we've been discussing in our recent videos. The first thing we're going to do is to define a very weak bottom-up parsing algorithm called LR0 parsing. And the basic idea here is that we're going to assume the stack contains a contents alpha and that the next input is token t, and that the DFA, this is the DFA that recognizes the viable prefixes, on input alpha, that is when it reads the stack contents, it terminates in some state S. And there's only going to be two things that this parsing algorithm needs to do. So if the final state of the DFA contains the item x goes to beta dot, well, what does that say? That says we've seen the complete right-hand side of x goes to beta on the top of the stack, and that furthermore, everything that's below the stack still says that x goes to beta dot is a valid or a viable, is a valid item for this state, meaning it's okay to reduce by x goes to beta. So if we see a complete production, dot all the way on the right-hand side, in the final state of the DFA, then we're just going to reduce by that production. The other possible move is a shift. If we wind up in a state where x goes to beta dot t and then some other stuff is a valid item, what does that say? That says that it would be okay at this point to add a t to the stack, and if t is our input, well, then we should do a shift move. Now, when does LR0 parsing get into trouble? Well, there are two possible problems it could have. It might not be able to decide between two possible reduce moves. So if any state of the DFA has two possible reductions, meaning it's seen two complete productions and it could reduce by either one, then there's not enough information to decide which reduction to perform, and the parse won't be completely deterministic. And this is called a reduce-reduce conflict. So again, this happens if a particular state has two separate items indicating two separate reductions. The other possibility is that the final state of the DFA, after reading the stack contents, might have an item that says to reduce and another item that says to shift. And this is called a shift-reduce conflict. So in this case, there would only be a conflict in a state where t was the next item in the input, but in that situation, we wouldn't know whether to shift t onto the stack or to reduce by x goes to beta. Let's take a look at the DFA for recognizing viable prefixes that we've been using for the last couple of videos. And in fact, this particular DFA does have some conflicts. So let's take a look at this state right here. Here we could either reduce by e goes to t if we were in this state, or if the next input is a plus, we could do a shift. So in this particular situation, if the next input is plus, we could either shift and use this item, or we could reduce and use that item. So this particular state has a shift-reduce conflict. Now, that's not the only conflict in this grammar, though. In this state here, we have a very similar problem. Here we could shift if the next input is a times, or we could reduce by t goes to int. And so this state also has a shift-reduce conflict. It turns out that it's not difficult to improve on LR0 parsing, and we'll present one such improvement in this video called SLR, or simple LR parsing. And this is going to improve on LR0 by adding some heuristics that will refine when we shift and when we reduce so that fewer states have conflicts. The modification to LR0 parsing that gives us SLR parsing is really quite small. We just add one new condition to the reduction case. So before, if we saw x goes to beta dot in the final state of our DFA, recall what that means. That means beta is on the top of the stack and is viable, and so it's fine to reduce. Now, we do have a little bit more information. So notice that the automaton here doesn't take any advantage of what's coming up in the input. This is based entirely, this decision here is based entirely on the stack contents. But it might be that it doesn't make sense to reduce based on what the next input symbol is. And how can we take advantage of that? Well, if you think about it, what's going to happen? We have our stack contents, and it ends in a beta, and now we're going to make a move where we're going to replace that by x. Okay? And if the next input symbol is t, so remember there'd be a vertical bar here and a t following, what does that mean? Well, that means that x has to come before t in the derivation, or in other words, t is going to follow x. And if t can't follow x, if t is a terminal symbol that can't come after the non-terminal x, then it makes no sense to do this reduction. So we only do the reduction if t is in the follow of x. We just add that restriction, and that is the only change to the parsing algorithm. So if there are any conflicts under these rules, either shift reduce or reduce reduce, then the grammar is not an SLR grammar. And just notice that these rules amount to a heuristic for detecting the handles. So we take into account two pieces of information: the contents of the stack, that's what the DFA does for us, and it tells us what items are possible when we get to the top of the stack, and also what's coming up in the input, and we can use that to refine our reduction decisions. And for those grammars where there are no conflicts, meaning there's a unique move in every possible state under those rules, then this heuristic is exact, for those grammars, and we just define those grammars to be the SLR grammars. let's consider how things have changed for our running example, the deterministic automaton for recognizing the viable prefixes of the grammar we've been looking at for several videos now. Recall that we had shift-reduced conflicts under LR0 rules in two states. Let's look at this state first, the upper state. So here we're going to shift if there's a plus in the input. That's what this item tells us to do. It tells us if there's a plus, then the right move is to shift. And so now the question is, when are we going to reduce? Well, we're only going to reduce if the input is in the follow of E. And what is the follow of E? Well, we computed it a long time ago, but just to remind you, remember that E here is the original start symbol of the grammar, so certainly $ will wind up in the follow of E. And the other possibility for the follow of E is closed paren, because here at this point in the grammar, closed paren comes right after E. And that's the only two possibilities. So what that says now, what that means is that in this particular state, we are going to reduce if either we're out of input or if the next token in the input is a closed paren, and we'll shift if the next token in the input is a plus, and in any other situation, we will report a parsing error. And so there's no longer any shift-reduced conflict in this state, and there's always a unique move for every possible input. The situation is similarly improved for the other state. So here we're going to shift if there's a times in the input, and we're going to reduce if the input is in the follow of t. And what is the follow of t? Well, recall we computed this again a long time ago, and I just happen to know what it is. And so I'll just tell you, well, it included everything in the follow of E. So $ and closed paren are in the follow of T, but also plus is in the follow of T because of this usage over here in the grammar where plus appears immediately after T. But those are the only things in the follow of T. And so now we're going to reduce only if we're out of input or if the next input item is a closed paren or a plus, and there's also no longer any shift-reduced conflict in this state. And so this grammar is an SLR1 grammar. Now, many grammars are not SLR. Should emphasize that SLR is an improvement on LR0, but it's still not a really very general class of grammars. So, all ambiguous grammars, for example, are not SLR. But we can improve a little bit on the SLR situation. We can make SLR parse even more grammars by using precedence declarations to tell it how to resolve conflicts. So let's revert to the most natural and also most ambiguous grammar for plus and times over the integers, and we've looked at this grammar before. If you build the DFA for this grammar, if you go through and build the DFA for the viable prefix of this grammar, you will discover that there is a state that has the following two items in it. One says that if we see E times E, that we have seen E times E on the stack, and that we can now reduce by E goes to E times E. The other one will say that if there's a plus coming up in the input, we should shift. And notice that this is exactly the question of whether times has higher precedence than plus. When you're in this situation, should you reduce, thereby grouping the two E's together here, grouping the multiplication operation first, or should you shift the plus, in which case you'll be working on that first since it's at the top of the stack. So in this situation, the declaration times has higher precedence than plus resolves the conflict in favor of the reduction. So we would not do the shift, and we would wind up with no shift-reduced conflict. Note that the term precedence declaration is actually quite misleading. These declarations don't define precedence. They don't do that directly at all. What they really define are conflict resolution. They say make this move instead of that move. It happens that in this particular case, because we're dealing with a natural grammar, a simple grammar for plus and times, that the conflict resolution has exactly the effect of enforcing the precedence declaration that we want. But in more complicated grammars, where there are more interactions between the various pieces of the grammar, these declarations might not do what you expect in terms of enforcing precedence. Fortunately, you can always print out the automaton. The tools provide usually a way for you to inspect the parsing automaton, and then you can see exactly how the conflicts are being resolved and whether those are the resolutions that you had intended. And I recommend when you're building parsers, especially if it's a fairly complex parser, that you do examine the parsing automaton to make sure that it's doing what you expect. So now we're ready to give the algorithm for SLR parsing. So M is our automaton, our parsing automaton that recognizes viable prefixes. The initial configuration is going to be with the vertical bar all the way to the left, so the stack is empty. This is our full input, and we append $ to indicate the end of the input. And now we're going to repeat until the configuration has just the start symbol on the stack and $ in the input, meaning all the input is gone, and we reduce the entire input to the start symbol. So an intermediate configuration will be written as alpha omega, where alpha is the contents of the stack and omega is the remaining input. And what we're going to do is we're going to run M, run the machine on the current stack alpha. And if M rejects alpha, if M says that alpha is not a viable prefix, then we're going to report a parsing error. We're going to stop right there. Now, if M accepts alpha, and it accepts it in a state, if it ends in a state with items I, and then we're going to look at the next input, call that A, and what are we going to do? Well, we're going to shift if there is an item in I that says it would be okay to see the terminal A next. Okay, so that's just our shift move. And then we're going to reduce if there's a reduction item in the set of valid items, and the next input can follow the non-terminal on the left-hand side. So these are just the two rules that we discussed before. And then we'll report a parsing error if neither of these applies. Okay? Now, one interesting thing about this algorithm, if you read it carefully and you think about it for a while, you'll realize that this step is actually not needed, that we don't need to check here for whether M accepts the stack or not. Because this step down here, where we report a parsing error, if neither of these steps applies, this already implies that we will never form an invalid stack, that our stacks will always be viable. The parsing errors will be caught at this line, and we won't pollute the stack with symbols that can't possibly result in viable prefixes. So in fact, this error check here is not needed. M is always going to accept the stack. Now, if there are any conflicts in the last step, meaning it's not clear whether to shift or reduce in some state for some input symbol, then the grammar is not SLRK. And K, again, is the amount of look-ahead. In practice, we just use one token of look-ahead. So typically, just looking at the next token in the input stream. Welcome back. In this video, we're going to do an extended example of SLR parsing. To review, here's the parsing automaton for the grammar that we've been looking at in the last couple of videos. And this is just the deterministic version of the non-deterministic automaton we built last time. And I've just gone through and numbered all of the states. So let's take a look at what happens when we parse the input int times int. And just to review, we've appended $ here to the end to indicate where the end of the input occurs. That's just an end of input marker. And because this is the beginning of the parse, we haven't seen any input yet, and so the vertical bar is all the way at the left-hand side of the input. So the machine begins in state 1, and there's nothing on the stack. The vertical bar is all the way to the left again, so the stack is empty, so it just terminates in state 1. And these are the possible items that are valid for the initial state of the parser. So among those items, we see that there are two that tell us that it's okay to shift an integer in this state. And of course, the first input is an integer, and so there are no reduce moves. All the other items in here also have their dots all the way at the left side of the item, so there's no possible reduce move in this state. The only thing we could possibly do is shift, and it's okay to shift an integer. So to summarize, on the initial configuration of the parser, the DFA halts in state 1. It never even gets out of state 1. It starts there and ends there without reading any input because the stack is empty. And the action that that state tells us to do is to shift. So that leaves us in the following state. There's an int on the stack, and we have a times coming up in the input. So what happens in that situation? Well, again, the automaton is going to read the stack. So starting from the bottom of the stack, we're in the start state, and then we read an int. There's an int on the stack, and we wind up in this state. And what does this state tell us we can do? Well, it tells us one possibility is to reduce by t goes to int. But again, we will only do that if the following input is in the follow of t. And times, which is the next input item, is not in the follow of t. So times is not in the follow of t, and so reducing here is not a possibility. That leaves only the other item to consider, and here we see that this item says we can shift a time. So if times is the next thing in the input, which it is, it's okay to shift. So the DFA halts in state 3, and because there's a times in the input, the move is to shift. And that puts us into this configuration where we have int and times on the stack. Times is at the top of the stack, int is below it, and we have an int coming up in the input. So what happens now? Again, the DFA is going to read the entire stack. So beginning at the bottom of the stack, the first thing it sees is an int, it moves to that state, and then it sees a times, and so it moves to this state. And now, in this particular state, what are the possibilities? Well, we can see, first of all, that there are no reduce moves. There are no items with the dot all the way at the right end. So the only possibility is a shift. And we could shift if the upcoming input's a open paren, which it's not. More usefully, we could shift if the upcoming input is an int, which is exactly what we see. So the DFA terminates in state 11, and the move in that state is to shift. And that puts us into this state where we have int times int on the stack, and we are out of input. We are at the end of the input. So let's see what happens on the stack int times int. The automaton reads it, int times int, and it winds up back in state 3. And state 3 tells us that we can shift if the next input item is a times, which it is not, or we can reduce if whatever is next in input is in the follow of t. And in fact, $ is in the follow of t, so the end of the input can come after a t on the stack, and that means it's fine to reduce by t goes to int. So once we do that, once we do the reduction, t goes to int, we wind up in the state int times t. That's our stack contents, and of course, we're still at the end of the input. So once again, the DFA is going to read the entire stack contents from the bottom to the top. First it reads the int at the bottom of the stack, then it sees the times, and then finally it reads the t at the top of the stack, and it winds up in a new state, state 4. And the interesting thing about this particular step is that the DFA took a different path through the state graph than it did the previous time, and that's because the stack contents changed. We didn't just add stuff to the stack, and so we didn't extend the previous path. We actually replaced some symbols or a symbol on the stack with a new symbol, in this case the non-terminal t, and that caused the DFA to take a different path. Now what does this item in state 4 tell us to do? Well, it says that we can reduce by t goes to int times t if whatever follows in the input is in the follow of t. And once again, $ is in the follow of t. And so we'll do that reduction. And now we're left with the stack contents just consisting of t. And of course, we're still at the end of the input. And let's see what happens now. So now, of course, the contents of the stack has changed even more radically. And so the DFA just goes off in a completely different direction. It reads t, winds up in this state. And this state says we can either shift a plus if there's a plus in the input. And again, there's no more input. Or we can reduce by e goes to t if if the end of the input is in the follow of e, which it is. And so the reduction move will be the one that we do. And now we have this stack contents consisting only of e. Let's see what happens in that situation. Now we make a transition to this state, state 2, and we only have one item, s prime goes to e dot. And so this is a reduce move. And again, $ is in the follow of s prime, because that is the start symbol. And since that is the start symbol, we accept at this point. So once we get to that item as our reduce move, we know that the input has been successfully parsed. In this video, we're going to wrap up our discussion of SLR parsing. We're going to give the full SLR parsing algorithm and also talk about some important improvements. The SLR parsing algorithm we discussed in the last video has one major inefficiency, and that is that most of the work that the automaton does when it reads the stack is actually redundant. And to see this, think about the stack. So we have our stack. This is the bottom over here, and this is the top of the stack over here. And what is going on at each step? At each step, we might shift something onto the stack, so we might add one symbol, or we might pop some symbols and push one symbol onto the stack. But basically, there's going to be some small number of symbols that change at the top of the stack at each step. But most of the stack stays the same. And then we rerun the automaton on the entire stack. And so this work is all repeated. Everything that stayed the same from the previous stack is repeated work, and then we do a little bit of new work just at the very top of the stack. And clearly, if we could avoid this, we could make the algorithm run much, much more quickly. The way to exploit the observation that most of the work of the automaton is repeated at each step is to simply remember the state of the automaton on each stack prefix. So we're going to change the representation of the stack. We're going to change what goes in the stack. So before we just had symbols on the stack, but now we're going to have pairs. Each element of the stack will be a pair of a symbol and a DFA state. Thus the stack now is going to be a stack of pairs, and whereas before our stack would have consisted just of the symbols, sim1 up to simn, now we're going to have the same symbols, but each one of them is going to be paired with a DFA state, and that DFA state is going to be the result of running the DFA on all the symbols to its left, so all the symbols below it in the stack. So if I think about my stack, again, if I draw a little picture of a stack as a line, then the DFA state here, let's call this state I, will be the result of running the DFA on the entire stack contents to the left of that point. And again, if I look at some other point in the stack, at the stack state that's stored there, that would be running the result of running the DFA on the entire stack contents up to that point. And one small detail here is at the bottom of the stack, we have to get started. We need to have the start state stored at the bottom of the stack, and we just store that with any dummy symbol. It doesn't matter what symbol we pick. So now we're ready to actually give the details of the parsing algorithm. And the first step is to define a table goTo, and this maps a state and a symbol to another state. And this is just the transition function of the DFA. This is the graph of the DFA written out as an array. Our SLR parsing algorithm will have 4 possible moves. A shift X move will push a pair on the stack. X is a DFA state, so that's named in the shift move now. And then the other element of the pair is the current input. And then we'll also have reduce moves, which are just as before. So to recall, a reduce move will pop a number of elements from the stack equal to the length of the right-hand side, and then it will push the left-hand side onto the stack. And then finally, accept and error moves for when we've successfully parsed the input and for when the parser gets stuck. The second parsing table is the action table, which tells us which kind of move to make in every possible state. The action table is indexed by a state of the automaton and the next input symbol. And then the possible moves are things like shift, reduce, accept, or error. So let's consider when we do shifts, if the final state of the automaton at the top of the stack has an item that says it would be okay to shift an A and goTo, that is, from this state, we could go to state J on input A, then the move in state I on input A will be to shift a J onto the stack. And think about what that means for a second. What that says is that we have a stack, and then the next input is A, and then at this point, it's okay to shift an A onto the stack. And furthermore, that the state of the automaton at this point is SI. Okay, so the state of the automaton at the top of the stack is SI. The next input is A. Remember that the goTo table is the transition function of the machine. So if we move the vertical bar over, if we shift that A onto the stack, well, now we don't just put A on the stack, we have to put a pair on the stack. And the question is, what machine state should go there? Well, it's going to be the state that we would reach from state I, from state SI, on input A, which the goTo table tells us in this case is state SJ. And for that reason, the action, when we terminate in state I, and the next input is A, is to shift the pair A, J onto the stack. The other 3 moves that go into the action table are things we've already seen. So if the final state of the automaton at the top of the stack has an item that says that we can reduce, and the follow condition requirement is satisfied, namely that the next input can follow the left-hand side non-terminal of the production, then in the entry I, when we're in state Si and we have input A, we can reduce by the production X goes to alpha. And there's one exception here. We're not going to do that reduction if the left-hand side is the special start symbol, the new start symbol that we add to the grammar S prime, because in that case, if the item that we're going to reduce by is S prime goes to S dot, and we're at the end of the input, then we want to accept. And any other situation is an error. So in any other situation, if we're in state I and we have the next input is A, well, we don't know whether to shift, reduce, or accept, and so that is an error state. Finally, here is the full SLR parsing algorithm. And I'm just going to walk you through it so that we can see how all of the ideas we've been discussing and all the various pieces fit together. Let's let our initial input be called I, and we'll just give it a name, and it's going to be treated as an array that we can index. The index will be called J, and initially it's 0, so that we're pointing to the first token in the input stream. We'll just assume that the first state of the DFA is called state 1, and that means our initial stack is going to have state 1 for the state of the automaton and some other dummy symbol that we don't care about in the first position. So the stack is just a pair with it says that we're in the start state of the DFA. And now we're going to repeat the following loop until we've either successfully parsed the input or we detect an error. And at each step, what are we going to do? Well, we're going to look at the next input symbol, and we're going to look at the final state of the automaton on the stack contents, and that's always the state of the pair that's on the top of the stack. And we're going to look those two things up in the action table, and that's going to tell us what kind of move to make. So let's just go through the moves in order. Let's consider the shift move first. So what happens? If it says that we're supposed to shift and go into state K, then what we're going to do is we're going to shift the input. That means we're going to take the next input symbol, or the current input symbol, excuse me, and we're going to push that onto the stack together with state K of the automaton. So that pair goes onto the stack, and we also bump the input pointer so that we're looking at the next character of input. Now, let me erase that so you can continue to read it. Now, what about the reduce moves? So this one's a little bit interesting. First thing we're going to do is we're going to pop a number of pairs off the stack that's equal to the length of the right-hand side. So we pop a number of items off the stack that's equivalent to that's equal to the right-hand side of the production. And then what do we push onto the stack? Well, we're going to push the non-terminal on the left-hand side onto the stack. And now the question is, what state goes onto the stack? What DFA state? Well, now that we've popped the stack, we can look at the new top state of the stack. So the DFA state at what is now the top state after we've done the pops will tell us what the final state of the DFA was on what is left of the stack. And then now that we're pushing X onto the stack, we want to know what state the DFA would go into on the transition labeled X. And so we use the goto table to look that up. The current top state of the stack on symbol X, where does the DFA go? That is the state that gets pushed onto the stack. And then finally, if the move is accept, we halt normally, and if the move is error, we halt and report an error or execute our error recovery procedure. One interesting thing about this algorithm is that it uses only the DFA states and the input. The stack symbols are not used in any really interesting way. And so we could actually get rid of the stack symbols and just do parsing with the DFA states on the stack. But that, of course, would mean throwing away the program, and we still actually need the program for the later stages of the compiler. So in order to do type checking and code generation, we still need to keep the symbols around. Now, simple LR parsing is called simple for a reason, and in fact, in practice, it's a bit too simple. The widely used bottom-up parsing algorithms are based on a more powerful class of grammars called the LR grammars. And the basic difference between the LR grammars and the SLR grammars is that look-ahead is built into the items. So what does that mean? Well, a LR1 item is going to be a pair which consists of a item, just like we saw before, and this means exactly the same thing as before, and a look-ahead. And in the case of an LR1 item, there's just one token of look ahead. If this was an LR2 item, there could be 2 tokens of look ahead in there. And the meaning of this pair is that if we ever get around to a state where we have seen all of this production, all of the right-hand side of this production, then it's going to be okay to reduce if the look ahead at that point is $, if it's the end of the input. And of course, there could be any other token in there, any other terminal symbol in there besides $. And this turns out to be more accurate than just using follow sets. Recall that at the point where a reduction decision is made in SLR parsing, we just look at the entire follow set for the symbol on the left-hand side of the production. And this mechanism of encoding the look-ahead into the items allows us to track at a finer granularity which look-aheads are actually possible in particular production sequences. And if you look at the automaton for your parser, actually it's not an LR1 automaton, it's an LR1 automaton, which is something very close to an LR automaton. It's a little bit of an optimization over a pure LR automaton. But anyway, it uses exactly the same kinds of items with this pair of a standard LR0 item and a look ahead. If you look at that automaton, you will see items that look like this, and that should help you in reading the automaton and figuring out what it is doing. In this video, we're going to work through a couple of SLR parsing examples. So let's do a very simple example. Let's consider the grammar S goes to SA or S goes to B. And what does this grammar do? It produces strings of A's followed by a B. So any number of A's followed by a single B. And notice that the grammar is left recursive, and recall that that's not a problem for a bottom-up parser. SLR parsers, LR parsers are perfectly happy with left recursive grammars. So let's begin by working out what the automaton for this grammar should be, what the parsing automaton should be. And recall that the first step is to add a new production to the grammar. We have to add a new start symbol that all it does has one production that goes to the old start symbol. And that's, again, just for technical reasons. Now, the start symbol, or sorry, the start state of the NFA of the parsing automaton is this item. S prime, our new start symbol, goes to .s, our old start symbol. And rather than build the NFA and then do the subset of states construction, let's just go ahead and work out what items must be in the first state of the DFA. So remember that all the epsilon moves in the NFA are due to moves that happen because we don't see a non-terminal on the stack, but instead see something derived from that non-terminal. So if we have a dot right next to a non-terminal, that means that there's an epsilon move in the NFA to all the items that have, for all the productions, all the first items for the productions of that non-terminal. What do I mean by that? I mean that this state would be an epsilon production to S goes to dot SA, so this is the first item in recognizing this production, so the dot's all the way at the left, and there would also be an item for the other production for S goes to dot B. All right, so that's the epsilon closure in the NFA of this start item, so this would be the first state. These three things, these three items would be the first state of the DFA. And now we have to consider what would happen on each of the possible transitions for each of the symbols that we might see on the stack. So let's think about what happens if we see a B. So if we see a B on the stack, then the only item that's going to be in that state is S goes to B dot. Okay, so it would be fine to see a B, and this would be the only item that was valid for the stack contents. Now another possibility is that we'll see an S. Okay, so if we see an S on the stack, what will happen? Well, we're going to go to a state that has two items. S prime goes to S dot, so that we've seen S on the stack, and we're ready to reduce by this production, possibly. And also S goes to S dot A. And now, clearly in this state, so actually let's talk about this state down here. the state here at the bottom, there are no more transitions possible. There's only one item in the state, and the dot's all the way to the right-hand side, so that state is completely done. In this state, the one over here on the right side, well, one of these items is complete, the dot's all the way at the right, but the other item still has an A, and so there could be one more transition out of this state to the item S goes to SA dot. All right? And now if we look at this, we see that for the most part, these states are in pretty good shape. So these two states, this one down here and this one over here, they only have a single item. And so there's no possibility of a shift-reduce conflict in those states. There's only one item, there's only one thing to do. The only possibility here in both of these states is to reduce. This state, the initial start state, has no reduce moves. So there's only shift moves here. So there can't be a shift-reduce conflict because there are no reduce items, no possible reduce actions, and there's no reduce-reduce conflicts for the same reason. So the only state of interest, really, from the point of view of whether the grammar is SLR1, is this middle state. Okay, and here we could either reduce by S prime goes to S dot, or we could shift an A onto the stack. And the question is, what is in the follow of S prime? So what can follow S prime in the grammar? And if we look back up at our grammar, we'll see that nothing can follow S prime. S prime is the start symbol, and so in fact the only thing in the follow of S prime is the end of the input. And so what that tells us is that we'll reduce by S prime goes to S if we're out of input, and otherwise if there is an A on the stack, if there's an A in the input, then we'll shift it onto the stack. And so this grammar is SLR1. There are no shift-reduce or reduce-reduce conflicts implied by this parsing automaton. Let's do another example, slightly more complex. In fact, let's just extend the previous grammar. We'll have a production. S goes to SAS. Okay, so now we have the non-terminal twice with an A in between. Or S can go to B, just like before. And now let's work out the parsing automaton for this grammar. And once again, we'll need to add a dummy start symbol to the grammar, and it will go, its only production will be to generate the old start symbol. And now let's begin working out what's in the parsing automaton for this particular grammar. And just like before, we're not going to go through the effort of constructing the NFA. That would be a systematic way to do it. One way to do it is the way we sketch, which is just to construct the NFA first and then do the subset of states construction. But this grammar is small enough and simple enough that we can work out directly what is in, what are in the states, what items are in the states of the DFA. So just like before, because the dot here is immediately next to the S, we know that we can, without consuming any input at all, make an epsilon transition in the NFA to the items that start the productions for S. So these will be in this, also in the DFA state. And that's it. We can't add any other productions here. So S is the only non-terminal, and we've added all the first items, initial items for S, and so that is the complete state. Okay? So just like before, one possibility is that we'll see a B on the stack, and so that would give us the item S goes to B dot, and that's the only item valid for that state. Another possibility is that we'll see an S on the stack, okay, in which case we'll make a transition to the state S prime goes to S dot, and S goes to S dot AS. All right, so we saw that same state before in the other automaton. Now we could also see an A, and what state would that take us to? And this is going to be a little different. In this state, we could have the item, or we will have the item SA dot S, but now notice that the dot is right next to S. So instead of seeing an S on the stack, we could also see something derived from S in the next position on the stack. And so we have to throw in all the productions for S. There's only two of them, but that means we could have the item S goes to dot SAS and S goes to dot B. All right, and then out of this state, now there are a couple of different possible transitions. We could see an S, or we could see a B. Well, if we see a B, then we wind up in this state over here. And if we see an S, well, what's going to happen? If we see an S, then we'll wind up in another new state. Where we have S goes to SAS dot. We've seen the complete right-hand side of that production. Or S goes to SA dot S. Actually, that dot's in the wrong place, so let's erase that, and let's put it in the right place. It's right here, before the A, not after the A. All right? And now we have to think about what happens in this state. So in this state, the only possible input is an A. And if it's an A, what's going to happen? Well, we're going to have S goes to SA dot S, and then we're going to have to add the initial productions for S again. And so that would just take us back to this state. And let me get the transitions labeled here. We go to this state on an S, and we come back to that state, the bottom state here, from the top state on an A. And I think, if we haven't made any mistakes, that is the complete transition system and all the states for this DFA. And now the question is this parsing automaton, is this the parsing automaton of a SLR1 grammar? And in order to answer that question, we have to look for possible reduce, and shift-reduce conflicts. Well, a quick scan of all the states here will show you or convince you that there are not any states where there are two possible reduce moves. So there can't be any reduce conflicts in this automaton. We can ignore states that only have a single item or states that have no possible reduce moves at all, because those are states in which there cannot be a shift-reduce conflict. And that means we can ignore these two states, the two states over here at the extreme left. So now we're left with these three states to think about. All right, so we look at this state last time. As before, the follow of S prime is just equal to the $sign. And so there's no shift-reduce conflict in this state, because on input A, we can only shift. We can't reduce by S prime goes to S. All right, now we're down to looking at these two states. And let's just consider this bottom state first. All right, so what does this state say to do? Well, this state says that, well, first of all, observe that the only transitions out of this state are on B and S, and there are no reduce moves in this state at all, so there's no possibility of a shift-reduce conflict in this state either. That leaves us with just this state to think about. All right, so now this state does have a reduce move. The first item here is a reduction, and that says that we should reduce by S goes to SAS if whatever comes next is in the follow of S. So we're going to need to know what is in the follow of S. Well, from S prime goes to S, we know that anything in the follow of S prime is in the follow of S. So clearly dollar is in the follow of S. And then from this part of the grammar here, we can see that A is in the follow of S. And then from this occurrence here of S, we know that since it occurs at the far right-hand side of the production, that anything in the follow of the right-hand side, the left-hand side non-terminal, is also going to be in the follow of S. Well, in this case, they're the same. It just says that the follow of S is a subset of the follow of S, which is trivially always true, and so it doesn't add anything new. And so we wind up with just the follow of S being these two things, $sign and A. But that poses a problem, because this says that if we see an A in the input, we should reduce. And this move here says that if we see an A in the input, we should shift. And so this state does have a shift-reduce conflict. All right, and so this grammar is not SLR1.